So now, so now we are getting ready for the Unit 5 test, and it says up here over sections 6, 7, and 8, but actually we're looking at sections 4 and 5 as well. That has to do with the properties of log functions and exponential functions. So actually I really want to say that this is sections 4 through 8 because we're going to have to use those properties as we solve these equations. In number 1, we see that this equation has an e as a base on both sides. And the rule here is if you have an equation that involves the same base, just a single number on both sides, then your exponents have to be equal. So I have 3x equals 2 minus x. So if I add x to both sides, I'm going to have 4x is 2, and if I divide by 4, I have x is 1/2. Example 2, same type of problem except for we don't have same bases. So what we're going to do is multiply these we're going to reduce our bases down to a single base. So notice that these are all powers of 2. So I'm going to write 4 as 2 squared, and that's going to be to the 2x power. And 8 is 2 to the 3rd power, and that's going to be to the x squared power. And then I have 2 to the negative 1st power. So this becomes, I'm multiplying my exponents here, 2 to the 4x times 2 to the 3x squared equals 2 to the negative 1st power. All right, so the next property I'll use is here, if I'm multiplying with the same base, I add my exponents. So I'm going to have 2 to the 4x plus 3x squared equals 2 to the negative 1st power. Now, since my bases are the same, my exponents have to be equal. So I'm going to write an equation based off my exponents. So I have 3x squared plus 4x equals negative 1. Or if I put it in standard form, plus 1 is 0. Now I can factor this, thankfully, and I can have 3x times x equals 3x squared, and 1 times 1 is 1. These are all positives, and if I just check that middle term, 3x times 1 is 3x, and 1 times x is 1x. 1x plus 3x is 4x. And if I set each of these factors equal to 0, 3x plus 1 equals 0. I subtract 1, 3x is negative 1, and x is negative 1/3. Over here, I have x plus 1 is 0, and x is negative 1. All right, so I have 2 solutions. In example 3, here I have a log sentence, and it would probably be easier to recognize this if this were an exponential sentence. So if I look at the log that's in base 3, if I use 3 as my base to the 2nd power, that's going to give me the 3x minus 2. All right, so 3 squared is 9 equals 3x minus 2. Add 2, I get 11. 11 is 3x, so x is 11/3. Number 4. Let's write this again as an exponential sentence. So I have 8 to the 2x plus 3 power has to equal 64. So now I'm just going to rewrite 64 as 8 squared. And then I have over here 8 to the 2x plus 3. And now, because my bases are the same, my exponents have to be equal. And I have 2x plus 3 has to equal 2. If I subtract 3 on both sides, I have 2x is -1. And then divide by 2, and x is -1/2. Number 5. This one, I'm adding two logs together that have the same base. So I have a property for that, which means if I have the same base, I can write it as a single log, log base 5, and these two parts right here get multiplied together. So I have x plus 6 times x plus 2, and that equals 1. Now I can write this as an exponential sentence where I have a base of 5 to the first power equals this right here. So I have 5 to the first equals, and I'm just going to multiply this out to save space. So this is going to be x squared plus 8x plus 12. Now I can subtract 5 on both sides because I have a quadratic equation. To put it in standard form, I'm going to subtract 5. So I have x squared plus 8x plus 7, minus 5 here. I'm going to factor, and this is x plus 7 and x plus 1. So my solutions are x equals -7 and x equals -1. All right, so because I'm working with logs, I have to have the log of something be greater than 0. All right, so if I were to plug in, let's just check -1. -1 plus 6 is 5, so this is positive. -1 plus 6 or plus 2 is positive, so this is a good solution. But if I plug in -7 here, I get the log base 5 of -1, and that will not work. All right, so although it works algebraically, this is an extraneous solution. That's an extra solution that doesn't work in the domain. All right, so my only real solution is -1. All right, so next one, we have log base 10 of something equals log base 10 of something else. And since they're both log base 10, I can say that these parts have to be equal. So I have 2x plus 1 has to equal x minus 2. So if I subtract x, I'm going to get subtract 1x, I'm going to get 1x, and if I subtract 1, I'm going to get is -3. And I'm also going to check this in my domain to make sure I don't have log of a negative number. And in this case, I do have a negative number, and I have a negative number here. This would be -5. This would be -5 as well. So this is no solution because -3 is not in my domain. So I would say that this is extraneous. It works, but it doesn't work in my domain. And because that's my only solution, I would say no solution. That was kind of a tricky one there. Number 7. Let's look at this in terms of the fact that it is a trinomial. And here I see these common 3 to the x powers. Let's do some substitution here. I can say that this is 3 to the x squared, and then this is 3 to the x minus 2 is 0. So let's say that v equals 3 to the x power. So I'm going to substitute v in here, and I'm going to have v squared plus v minus 2 is 0. I'll factor that, and I have v plus 2 and v minus 1 is 0. So v is negative 2 and v is 1. And then these are my solutions for v, but I need to find out what x is. So I'm going to plug v back into how we substituted in there. And I'm going to say, all right, negative 2 equals 3 to the x power. And from the couple examples that we've done in class, we should remember that 3 to any power is always going to be greater than 0. So I cannot get negative 2 as a solution. So I'm going to cross that out and say it's extraneous. And then I'm going to check 3 to what power is 1. I'm plugging in 1 for v here. And just thinking about this, any number to the 0 power would give me 1. So x has to equal 0 here. Number 8 is very similar. I have a trinomial again. Look for those 3 parts with some kind of similarity here in terms of our bases. Now 25 and 5 are not the same base, but I can write 25 as 5 squared to the x power minus 5 to the x plus 1 power plus 4 is 0. So this is 5, if I want to say this is 5 something squared, I'm going to say this is 5x that's being squared. And I have another 5x here, 5 to the x power. And the rule for adding my exponents is I have the same base. So this is really, and I'm going to do this up here, 5 to the x times 5 to the first. Same base, I'm adding my exponents, but really this is a multiplication problem. So this would be times 5. And if I say that v is 5 to the x power, and I'm going to substitute here, this would be v squared minus 5v plus 4 is 0. So now I'm going to factor this. And the numbers that multiply to be 4 and add to be negative 5 are v minus 5 and v plus 4, or minus 4. Multiply, whoops, that'd be a 1. That'd be a 1 here. Negative 5 times negative 1 is positive 4. How about if I go back and let's rework that one. Numbers that multiply to be 4 and add to be 5. So 4 times 1, negative 4 times negative 1 is positive 4, and then they add to be positive 5, or negative 5. Whew. So if I solve this, this is v equals 4, and v is 1. So this one is kind of easy because if I'm substituting back inside here, v is 1, so I have 5 equals boy, I'm really blowing this one. I have 1 equals 5 to the x. And we know that 5 to the 0 is 1, so x is 0. That's one solution. Now my other solution is v is 4. So I'm going to plug in 4, and that equals 5 to the x power. All right, so when I'm solving for x and it's in my exponent, I need to log or natural log both sides. All right, so it doesn't really matter which one you use. I'm going to do ln 4 equals ln 5 to the x, and that brings the x out in front. X ln 5 equals ln 4. So x is going to equal, if I divide both sides by ln 5, I have the natural log of 4 divided by the natural log of 5. And that is another solution. If you're playing around with your calculator and you want a value for that, it's approximately equal to 0.861. All right, flipping on to the next page, we have some story problems that involve interest. So the first one is, how much would we make if we invested $600 at 5% compounded monthly after 3 years? All right, so we have a couple of formulas. First of all, I equals rate, principal times rate times time. Then I have the final amount equals the principal times 1 plus r over n to the nt. And then this is if it's compounded in sections during the year. So if it's compounded monthly or daily or weekly, we would use this formula. This one, if it's just compounded once during the year, that'll tell us how much interest we get, but the final amount would be A equals principal plus interest. Okay, that's kind of a two-step if you're only working with one time per year. This is multiple time per year, and we also have a final amount is the principal. If it's compounded continuously, we have P times E to the RT. All right, so in number 9, it says that it's compounded monthly, so that means the number of times per year is 12. Okay, 3 years means our time is 3. I'm going to zoom back out here. And 600 is our principal, and 5% is the same thing as 0.05, which is our rate. So because I am compounding my interest monthly, I need to use this formula. So how much would you make? This, for me, I'm thinking how much is in your account. So my final answer, my final value, will be 600 for my principal times 1 plus my rate is 0.05 divided by n, which is 12, times 12, or to the 12 times 3 power. All right, so if you put this directly into Desmos, that means that in your account you're going to have $696.88. Okay, always round to the nearest penny. Okay, so from this amount, how much is the interest? That's actually what I would make. I don't think that's the wording that this is intended, but I would make how much over 600? $96.88. Number 10, how much would you make? And we're going to use the same principal from above where the principal is $600. If we invested at 12%, so my rate is 0.12, compounded continuously for 16 years, so time is 16. Now, because I'm compounding continuously, I'm going to use this formula with the E in it. So I have A, how much would I make? That's the final value. My principal is 600 times E, my interest rate is 0.12 times time, which is 16 years. And when I calculate that, I get a value of $4,092.58. All right, number 11 is a question of exponential growth and decay, 11 and 12. So it says that a culture of bacteria obeys the law of uninhibited growth. Well, that means that we're going to use the formula A over time equals A sub 0 times e to the kt power. All right, so that's exactly the same formula as this is up here. Okay, so this could be A over t or n. We could use a number, we could use the variable n, and it means the same thing, so I don't care which one you use. So 11, if a culture obeys this law, if we have 500 bacteria are present initially and there are 800 after 1 hour. Okay, what we're going to need to find here, if I look at just part A, I know I start with 500, so that's my A sub 0. My final amount is 800, and my time is 1 hour. So I need to plug this in. So I'm going to have 800 equals 500 times e to the kt power. So this is, and t is 1. So this is asking me to find k. What is the rate of growth? So I'm going to divide both sides by 500. So I have 8/5 equals e to the k power. Now to get the exponent out, the variable out of the exponent, because I have base e, I definitely want to do natural log here on both sides. So I have ln of 8/5 equals, and when I do ln of e to the k, I'm going to bring k out in front, and ln of e just cancels. So k is the value of ln of 8/5, and that value is 0.470. So this is my rate of growth. In part A, it's asking how many will be present in the culture after 5 hours. Well, we had to find our rate of growth to answer that. So now if my time is t is 5, and my rate is 0.470, and my initial value is still 500, how much will be there at the end? So this will be 500 times e to the 0.470 times 5. All right, so calculating that, it will be 5,242.78. Okay, so that actually is the answer to part A. Part B is asking us, how long is it until there are 20,000 bacteria? So my A value here is 20,000. I'm finding the time. I still start with 500. E to the same rate, which is 0.470 times time. All right, so first thing I need to do is divide both sides by 500, and I get 40 here. 200 divided by 5 is 40, and this is e to the 0.470t. And again, I'll natural log both sides. So I have ln 40 equals 0.470t. Divide by 0.470. And t is 7.85 years. Last one, number 12. Same concept. We're looking for the half-life of radium, and they tell us that that is 1,690 years. We have 10 grams, so this is going to be our amount at the beginning, or that's how much is present now. How much will be present in 100 years? All right, so we have to find the rate of decay. So this right here tells us that however much we have in 1,690 years, we're going to have half that amount. So if I start with any amount, I'm going to end up with half that amount. And that equals times E to the K, which was what we're finding, and the time it takes to get to that half of amount is 1,690 years. All right, so I'm going to divide both sides by A, and I have 1/2 equals E to the 1,690 times K. Now to get the 1,690k out of the exponent, let's do the natural log on both sides. So I have ln, and I'm going to write 1/2 as 0.5, equals 1,690 times k. So k will be, and this is going to give us our rate, and I'm expecting our rate to be negative because this is going down. I'm only going to have half the amount left than what I started. So when I divide ln of 0.5 divided by 1,690, k is negative 0.00041. All right, so that is my rate of decay. Did that answer the question? It did not, because this is telling us we're going to start with 10 grams, and we want to know how much will be present in 100 years. So my time is 100. My rate of decay, or K, is negative 0.00041. So now I put this back into this equation. So I'm starting with 10 times e to the kt. So this is negative 0.00041 times 100. And actually, I know that if I multiply these together, this actually becomes 10 times e to the negative 0.041. I just multiplied these together. But you could have left them separate and multiplied them on the calculator. And once you do this, 10 times e to the negative 0.041, it will tell you that you have 9.598 grams. All right, and that is it.